For thousands of years, people have used rocks, sea, air, and plants to obtain materials. Humans learned how to react these materials in the right amounts together to form new substances such as polymers, dyes, and fabrics. The relative masses of atoms and molecules are important in forming these new substances, so let's learn more about how to calculate them and use them in chemical equations. We all know that elements are made of atoms, and that all atoms are similar in their basic components. All atoms contain three major components: the positively charged protons, neutrally charged neutrons, and negatively charged electrons. Different elements have different masses due to the different number of protons, neutrons, and electrons presented in each element. For example, each copper atom consists of 29 protons, 35 neutrons, and 29 electrons. One single carbon atom contains 6 protons, 6 neutrons, and 6 electrons. And for helium atom, each atom consists of 2 protons, 2 neutrons, and 2 electrons. We simply can't weigh atoms to know their masses. Atoms are so tiny. To solve this problem, scientists set the mass of carbon-12 to be exactly equal to 12 units. And we compare the mass of any other atom of any other element to the mass of one carbon-12 atom. By that, the scientists were able to set one atomic mass unit to be exactly equal to 1/12th the mass of one carbon-12 atom. This means one atomic mass unit, AMU, is equal to 1/12th the mass of one carbon-12 atom. From that, we can compare the relative atomic mass of any element to be equal to the average mass of all atoms in an element compared to 1/12th the mass of a carbon-12 atom. Or in other way, the relative atomic mass is the ratio of the average mass of the atom to the unified atomic mass unit, AMU. For example, experiments showed that, on average, the mass of one hydrogen atom is 8.4% the mass of carbon-12 atom. This means if the mass of one carbon-12 atom is said to be 12 atomic mass units, AMU, the mass of the hydrogen must be equal to 8.4 multiplied by 12 divided by 100, because it's a percentage, which is equal to 1.008 atomic mass unit. Another examples, similar experiments showed that the atomic mass of oxygen is equal to 16 atomic mass units. The atomic mass of chlorine is equal to 35.5 atomic mass units, and the atomic mass of iron is equal to 55.85 atomic mass units. Now, if we looked at the periodic table, we should see the relative atomic mass of elements below the element symbol. If you looked at the carbon in the periodic table, you should expect the atomic mass of carbon to be equal to 12, the oxygen equal to 16, and the chlorine equal to 35.5. Instead, what you see, 12.01 for carbon, 15.999 for oxygen, and 35.45 for chlorine. The reason for the difference is that most naturally occurring elements, including carbon, have more than one isotope. For example, hydrogen has 3 isotopes. Hydrogen 1 isotope with atomic mass equal to 1.0078 atomic mass units, and the relative abundance equal to 99.98%. Hydrogen 2 isotope with atomic mass unit equal to 2.0141 atomic mass units and relative abundance of 0.015%. The third one is the hydrogen 3 isotope, which is presented as traces. That is why we consider the relative abundance of hydrogen 3 isotope to be negligible. So, the relative atomic mass you often see in the periodic table is equal to the total of the sum of the relative atomic masses of all isotopes for hydrogen divided by 100, which is equal to 1.0078 multiplied by 99.98 plus 2.0141 multiplied by 0.015 all divided by 100, which is equal to 1.008. This is a number you often see in the periodic table. Notice it has no unit. Another example, carbon has two isotopes. The most abundant carbon-12 isotope with atomic mass equal to 12 atomic mass units, with atomic abundance percentage equal to 98.90%, and the carbon-13 isotope that has atomic mass equal to 13.00035 atomic mass units, with abundance percentage equal to 1.1%. By that, the relative atomic mass of carbon is equal to 12 multiplied by 98.9 plus 13.00035 multiplied by 1.1, all divided by 100, equal to 12.01. This is the number you often see in the periodic table. On the other hand, oxygen has three isotopes, isotopes 16, 17, and 18, with atomic masses equal to 15.99, 16.999, and 17.999 atomic mass units. And the relative abundance of the three isotopes are equal to 99.75, 0.037, and 0.204%. The average atomic mass of oxygen is equal to the sum of the three atomic masses 16, 17, and 18, multiplied by the percentage abundance divided by 100, which is equal to 15.39. Now moving to the relative molecular mass, which we give the symbol Mr. We all know that molecules are made of atoms. For example, water molecule is made of 2 hydrogen atoms and 1 oxygen atom. Hydrogen chloride molecule is made of 1 hydrogen atom and 1 chlorine atom. The mass of the relative atomic masses of all atoms in the molecule gives us the relative molecular mass of a compound. The relative molecular mass of a compound is dimensionless as well, which means it has no unit. For example, methane molecule has 1 carbon atom and 4 hydrogen atoms. The relative molecular mass of methane is equal to the sum of the relative atomic masses of carbon, 12, multiplied by the number of atoms, which is equal to 1, plus the relative atomic mass of hydrogen, 1, multiplied by the 4 atoms, equal to 16. So the relative molecular mass of methane is equal to 16. What if we have a compound containing ions? The relative formula for ionic mass will be similar to the relative molecular mass. For example, magnesium hydroxide contains magnesium ion and 2 hydroxide ions. The relative formula mass value is equal to 1 multiplied by the relative atomic mass of magnesium plus 2 multiplied by the relative atomic mass for 1 oxygen and 1 hydrogen. By that, the relative formula mass for magnesium hydroxide is equal to 1 multiplied by 24.3 plus 2 multiplied by the sum of 16 plus 1, which is equal to 58.3. Notice it didn't make a difference if we have atoms or ions.